O'clock. All right. Perfect. Okay, so let's get started. Hello everyone, welcome to my general exam talk. So my name is Cindy, and before we begin, I'd like to take a moment to thank my advisor, Olga, for always being supportive, and Aji and Simon for being on my committee. Thanks for your time, and thanks everyone for being here. Yeah. So this talk summarizes my research interest on the data-centric multimodal machine learning, and more specifically, vision language dataset distillation that I have been explored recently. So this talk will cover, I will cover like these 5 different sections. I will start with a motivation, and then previous work, method, experiment, and conclusion. So let's start with the motivation. The 2 questions I want to ask here for the motivation part is, what is data-centric multimodal machine learning, and why is dataset distillation important? So the dictionary definition of multimodal is that it has this multiple modalities, and a more research-oriented definition is that multimodal is a science of heterogeneous and interconnected data. So information presented in like different modalities often have diverse qualities or structures or different representations. And data is a cornerstone of innovation in the multimodal machine learning. So we can say from 2014 to now, there are so many multimodal data sets coming out, for example, like Flickr 30K, COCO, Visual Genob, Line 400 million/5 billion, and like Datacom, those type of data set. So the scale of vision language data set has been growing bigger and bigger over time, and they can reach millions or sometimes even like billion levels. But the data is often very complex and too noisy. So we often face challenges such as like how to find specific information from this like massive data set more efficiently. And usually those information, they are included in certain low dimensional structure and may only depend on a small or sparse subset of the massive data set. So data-centric multimodal machine learning, they often focus more on like understanding and improving multimodal data, as well as more like systematically building better data for multimodal tasks. And next, so data can be seen as a combination of useful information and noise. So ideally, we want to extract and identify and extract the like critical information from the data set. So how can we do that? How can we obtain this information? So we propose that dataset distillation is one promising solution. Okay, so let's talk about what is dataset distillation. So let's take CFAR10 as an example here. So CFAR10 consists of 50K training images, and they are divided into 10 different classes. For example, cars, cats, or dogs, things like that. So each class have 5,000 images in the training set. But now in the distilled CFAR10 data set, instead of 5,000 images, we can end up with just 1 or 10 distilled image per class. So the model trained on this like small synthetic data set can still have a similar classification performance. And let's take a closer look at the distilled data. So this is the distilled CFAR10 from 10 images per class. So all those 10 images are the dog images. So dataset distillation aims to learn this small synthetic data set that can preserve most of the information from the original data set. And the model trained on it can still have a similar test performance as the one that trained on the original data set. And here's a kind of a loose definition. So approaches that aim to synthesize tiny and high fidelity data summarizes which distill the most important knowledge from a given target data set. And so this is fundamentally a compression problem, and more specifically like pragmatic compression. So we're finding this equivalent bit that can represent the entire data set. And such distilled summaries optimized to serve as effective drop-in replacement of the original data set for efficient and accurate data usage applications. So that means like we can achieve like equivalent model performance, but with significantly less data, and we can have like faster training time or lower computational costs without like sacrificing too much of the accuracy. So due to this like synthetic and highly condensed nature of the distilled data set, we can have all those type of application, for example, neural architecture search, federated learning, continual learning, and differential privacy. So additionally, dataset distillation can also enable like efficient knowledge merging across different data and also like different models. So by distilling like multiple data set into a single synthetic data set, we can leverage the collective knowledge from various like sources. Next, I will talk about the previous work. As we seen this like distilled CFR10 just now, so traditional dataset distillation method, they primarily focus on image classification tasks. And so the previous approach can be roughly categorized into these 4 different ways. For example, meta model matching, people also call it meta learning matching, and gradient matching, distribution matching, and trajectory matching. So although those like direct information extraction is not feasible, we can match the byproduct of the target like original data set and also our distilled data set, like the byproduct of all those like, for example, gradient or distribution or trajectory perspectives like this. And so I will talk about 2 previous work in this section. So from the meta model matching framework perspective, it formulates the dataset distillation task as a bi-level meta learning problem. And for example, if we have a large scale dataset, for example, the like X here is the image and Y is the label associated with it. And in the large scale dataset, we have N pairs of data. And our goal is to have this like small synthetic dataset D hat. It consists of the X hat and Y hat. They are the distilled image and label. So the distilled data set have only like M samples, and M is much smaller than the N here. So suppose we have the model like F of theta, and also we use the generalization loss to evaluate how good the distilled data is. So dataset distillation has this like a bi-level or meta learning formulation. So the inner level is basically trying to train this model on the distilled data, and outer loop will optimize the distilled data. Yeah, so we train those like several different neural network parameterized by the theta on the data set D hat, and then we compute the generalization loss on the real data D. So here the F D hat theta is the neural network parameters optimized by a learning algorithm like F, and with the model initialization theta, and also the distilled data set like D hat here. So the D hat will be the input to this. Yeah.
We still need to train a model on.
Basically for the meta learning framework, we don't need to do that. But like for trajectory matching, like other type of method I will explain later, they have to have like a expert buffer point. Yeah. So the generalization loss here is like it is a noisy objective with the stochasticity coming from random noise, random model like initialization, and also like inner learning algorithm. So we can basically minimize this expected value of this loss, where we denote it as like the FD hats here. So another work that I want to mention is the trajectory matching, and it inspired our method. So trajectory here refers to the long-range training dynamics of the network. First, the model is trained on the entire data set. So this is the X-bar trajectory. And then, so as it learns, we record its trajectory, which is the sequence of the parameter changes. So this is the like X-bar trajectory, and it represents the ideal learning process. And next, we will learn this. The yellow one is the teacher, the student model. So we can train the student model on the distilled data set. By updating this distilled data set, we can make sure that when the student model is trained on it, the parameter change will closely follow the X-bar trajectory. Yeah. And next, I want to give a quick comparison of our work and the previous work. So as I introduced before, that previous work mostly focused on image classification, dataset distillation. So the X and Y in the previous notation, they represent for image and label. But compared to those previous work, they often synthesize information for each class one by one. We focus on distilling vision language data set, which has no discrete class here. And so what does vision language data set look like, or what's unique about it? So here I'm giving an example from Flickr 30K. It's the image is like a dog, and then the text. Let's read the first caption of this data sample. So a dog wearing a green sweater and fanny pack walks on a snow-covered field. So let's say what are the informations included in this data sample? For example, dog, walks, green sweater, backpack, and also like snow. So so we can say from this sample that this data sample contains much more information compared to just one like dog with a label dog, and there are also a lot more objects. Yeah. So what are the common approaches to select the most critical information in this vision language dataset? And the simplest way is just by selecting a small subset of the real image text pairs. So so we can do this by just core set selection, which aims to select a diverse subset of the real data. So I will introduce like 3 core set selection methods here quickly. The first one is herding. So herding selects pairs based on the similarity. So we use the pre-trained like image and text encoders to extract its features and find the original dataset center. So we iteratively adding pairs that helps the core set center getting close to the dataset center. And the second part, the K-center baseline. So K-center, on the other hand, it will pick the training examples that are far apart. So it starts with a random point and keeps adding the forest pairs until it reach a threshold, like a K number, but this can be computationally heavy. And then last one, so first, the forgetting event. The concept of forgetting event is that when the model correctly predicts an example in one epoch but fails in the next one. So forgetting is basically like focus on example that are most consistently learned by the model, and it tracks when the model forgets a learned example and picks the pairs based on the least forgetting events. So about our task, we are no longer only focused on the image distillation, especially like low resolution images. For example, the CIFAR10 example we said before that they only have like 32 times 32 images. They're pretty low resolution. So properly defining the distilled data set and update it is a challenging part of our task. So what we want is a smaller set of image and corresponding text, and we are trying to like distill both of them. Yeah. So in this work, we create the first dataset distillation method for vision language dataset. So given a dataset that consists of a set of images with the corresponding language description, our methods would create a set of like synthetic image and corresponding like synthetic text embeddings, which can be used to train the model and learn the correspondence between the new image and the text, new text description. So there are mainly three challenges of our vision language dataset distillation. So the first one is complex cross-model relationship. So this is because like previous dataset distillation method, they often contain this like a discrete set of classes to ground the distillation process. But we don't, so we don't have this anymore. But like instead, we would have the more complex cross-model connections as well as like redundancies. So it requires us to have a co-distillation approach to capture this like interdependencies more effectively. And then the second part is the discrete text optimization issue. So unlike those continuous data, text is inherently non-differentiable. So it is very challenging to make like direct gradient based optimization on this like discrete text tokens. So we need to figure out what kind of design we want to have in order to perform this like gradient based optimization on text. And the last one is the heavy computational cost. So it comes from, this part comes from the high resolution images we will use in the vision language dataset. And also the models that people usually use in the vision language test are a lot more complex. It's no longer just like 3-layer convolutional neural network anymore. Yeah. So now let's talk about our method. Here's an overview of our method pipeline. So our approach focuses on this creating this distilled data from with both image and text. So in our setting, each pair comes with one image and one sentence. So this is more efficient compared to the original setting. Like they always have one image and 5 sentences. Yeah. So similar to what we talked about before, we also define large scale data set as the D here. It contains n pairs of X and Y. X here refers to the images and Y are the text. Y are the text embeddings here. So the goal of our distilled pipeline is basically the input data will be the large scale data set, and we want our output to be the small synthetic data set. So one more thing I want to mention is that those pairs, they are not just scaled down core set of the original data set. They are like the synthetic data that will capture the critical information from this like vision language connections in the data set D. Yeah. So for the distilled image optimization, we will directly optimize on the the pixel values of the distilled images. But how do we handle this text optimization? So we initialize the continuous sentence embeddings using a pre-trained BERT model and update the distilled text in the continuous embedding space. And now, like, given the input data, how do we encode the image and text features? So let's consider a vision language model. We have the image encoder, F theta of image here, and also the text encoder G theta of text here. Both come with one linear layer in the end. So for the text branch, we will have the text encoder part pre-trained and frozen. And for both of the projection layer, they will be trainable and they will train from scratch. And for the image part, we will keep it both like pre-trained and trainable. Yeah. So this model can be trained by optimizing the similarity loss, which encourage the alignment between image and text embeddings. And more specifically, we will use contrastive loss, which will bring the like positive pairs close together and push the negative pairs further apart. So this is a pretty common approach in like the multimodal task for effectively learning the shared embedding space. Yeah. So then we jointly learned this encoders F and also like G, so such that the cosine similarity of all of the incorrect image text pairs will be the cosine similarity of them are high, and but for the n squared minus n incorrect pairs will be low, and the cosine similarity is defined as the alpha here. So we then compute the contrastive loss, which include the image to text matching loss and the text to image matching loss. And that's so I will talk about our approach. It has like two stages. So the first stage is the expert training stage. So we will save both the image and text expert trajectories to the buffer. So we basically will train the multiple models for T epochs on the full data set D. And then we have this expert training trajectory set, the tau star here with each trajectory, it record how my model changed from the beginning to converge. So for the multimodal setting, we use this contrastive loss as we just introduced. So each expert trajectory, they are recorded from the beginning of the training onto a converge. And for the second stage, the distillation stage, we will randomly sample the M image text pairs from the original data set to initialize the distill data like D hat here. And we train the student model on the distilled data using the same contrastive objective. Here we use a phi trajectory matching loss. It's designed to make sure that the student trajectory aligns with the expert trajectory. And then we use a gradient to back propagate onto the image pixel and text embedding space of our like distill data. And that's how we update our distill data set. Oh, yes.
Just a quick question. When you reported the trajectories, the things that you report in a trajectory, are they sort of per step and with mini batches, or are they using the full data set?
Yeah, so we use the epoch, like basically after one epoch, we save the model weights. Yeah.
There's something that I might have missed, but if you have multiple expert models in the.
Yeah. That's right.
And then the student models, we have like one student model per expert that you're matching, or.
So for the expert model, we have, for example, we save like 20 expert trajectories in the buffer. And for the student model, we will, I will talk like next step, like about, so we randomly sample one starting point, and then we basically the expert trajectory will randomly sample one trajectory to use. So the student, yeah, the student trajectory is just one, like we want to distill the data using the, like how the student model works. Yes, so like you can randomly sample, it could be the same one, but it will be random sample.
I have a question that I say that. For the thing this before,
yeah.
Are you doing more than learning to learn the joint embedding and the classification?
Say that one more time.
For here, you're doing what
So yeah, so the contrastive learning is used to basically we like that's the kind of like yeah, it's like replacing the previous classification loss. Yeah.
For a given M, how does force and compare to the estimation method?
Yeah, so for example, were you asking like about the setting?
Yeah, if I use number of.
Oh,
Yeah.
right. Yeah, for example, I will talk about that in the experiments. Oh yeah, so we usually do like 100 pairs, 200 pairs, or like so which is like less than 1% of the data in the original data set. Okay, yeah, all right. So here, let's talk about the phi trajectory matching loss. So we sample the expert trajectory like tau star and a random starting epoch, for example, like the S here, to initialize both the theta image and theta text. So we train the student model on the distill data for like R hat steps, and to obtain this like theta R hat theta hat image like S plus R hat, and also the corresponding text one. Yeah, so the goal is to match the target parameter after R steps on the expert trajectory. They are denoted as the blue part here. So the trajectory loss is computed on the accumulated difference between student trajectory and the expert trajectory. And then we will update the distal data set by like back propagating through the multiple gradients descent updates to the D hat. The multiple steps are like the R hat steps here. Yeah. So this is a visualization, and the red line here, they are the student trajectory segments from a random starting point on the expert trajectory. And the trajectory matching loss would encourage our student model, student trajectory to match the target expert trajectory after certain distillation steps. And so next one, for complex image encoders like vision transformers, the bi-trajectory matching actually doesn't work well because of these two reasons, like high dimensionality of the embeddings and also the large number of parameters. So we consider, consider this a linear layer with M input units and M output units. So the weight metric for this layer has a dimension of M times N. So the output Y will be the W times X, like plus like bias and stuff. Yeah, so let's say if the input units are like 800 and output is 3,200, then we would have this many weights. So that's a pretty large number of parameters. And we introduced a low rank adaptation matching here for like more complex model like VIT. So before we jump into low rank matching, let's talk about what is the like low rank adaptation. So low rank adaptation is basically we keep the pre-trained model fixed and introduce these two metrics A and B. So the output will be Y equals to WX plus the A times B times X. So LoRa is effective for like fine-tuning pre-trained models, and it will introduce like trainable low-rank matrices to the weight matrices of like specific layers of the pre-trained models. So during the like fine-tuning with low-rank adaptation, we'll keep the the pre-trained weight part fixed and only train on this like A and B. Yeah. So let's use the same example as we talked about before. We still have this 800 as the input unit and 3,200 as the output unit. So metric A would have the shape of 800 times R, and metric B would have the shape of R times 3,200. So the R here is more like an empirical number. You can set it to like 1, 2, 3, 4. Yeah, so now the parameter is much more, much smaller compared to the original parameter. So LoRa has demonstrated that like to fine tune a pre-trained model, there's no need to modify like every single weight in each layer. So instead, we can introduce a method to learn more lower dimensional and task specific representations of the layers weights. So we further propose the low rank adaptation LoRa this matching. So we basically will just match the trajectories of only a small subset of the model's parameter through this low rank matrices. And for example, the VIT model we use is the VIT based patch 6x4, and it has 86 million parameters. But with the LoRa and the rank equals to 4, the parameters is reduced to 18 millions, and it cuts down like basically 78% of the parameters. So this allows for more efficient adaptation of the model with like minimum additional parameters, and we can focus on a smaller set of the parameters and efficiently optimize the trajectory loss during the like distillation while still maintaining the capacity to save the critical information. So let's revisit the challenges we mentioned at the beginning. So the first one, complex cross-model relationships. For this part, we solved it with the bi-trajectory matching method with like contrastive loss. And the second one, discrete text optimization issue, we adapt the discrete sentence to continuous sentence embeddings and optimize on the embedding space. And the last one, heavy computational cost. We've used the fine-tuning method with low-rank adaptation to achieve this. All right, so for the experiment section, I will talk about our experiment setups. First, so we evaluate our method on Flickr 30K and Cocoa, these two data sets. Both of them, so each one has like, so Flickr 30K have 30K images, and the Cocoa one has 328K images. So with like 5 captions associated with each image. So those data sets, they are very widely used in the previous work in like vision language data set tasks. Yeah. And then for the task, we conduct like 2 sets of image text retrieval tasks. One's the image to text retrieval and also text to image retrieval. So more specifically, we during the testing phase, we take one data modality as a query set to retrieve another data modality. So given the image or text query, the goal of each cross-model retrieval task is to find the nearest neighbors from the text or image database. And then we evaluate our model's performance using this like R at K metric, and K equals to 1 or 5 or 10. So this is just, we're trying to compute the fraction of times the correct result is found among all those top K items. Yeah, and the model we use for the image encoder, we primarily use the NFNet and also vision. NFNet is a non-frame net here, and it's also very widely used in vision language models, for example, like Flamingo. And another image encoder we use is the vision transformer. So for the language encoder part, we have the BERT model. And then here are some results. So we considered like different numbers of distilled pairs, for example, 100, 200, 500, and 1000. And we reported their like image to text and text to image retrieval performance on both Flickr 30K and Cocoa dataset. So here we can say that, like for example, on Flickr 30K, the best core set selection method can, like for example, selecting 1,000 image text pairs for training, they would only achieve like 5.6% image to text retrieval accuracy for R1. But in contrast, our like dataset distillation method almost doubles that number to 9.9% with just 100 training pairs. And here are more visualizations of the image text pairs before and after distillation. So we can say that for the text here, we visualize the text using the nearest sentence decodings in the training set that corresponding to the distilled text embeddings. Here are more visualizations. On the left, the blue ones are the image text pairs before the distillation, and on the right, this part are the examples after distillation. So another part we find out is, let's recap on the previous like CFR10 example. The distilled dog actually look nothing or like look very different than the original dog in the original data set. So we also find that like increasing the learning rate and distillation steps sometimes would lead to more noticeable changes in the distilled image. But however, the higher learning rate or longer distillation steps sometimes doesn't lead to better performance. So even if the images appear to deviate more from the human perception perspective. So we want to say that the changes in the image pixel alone that may not reliably predict the distillation performance. So it is rather a measurement of how strong the distillation is. So more distorted images may suggest uneven pixel changes.
How are you getting these ones?
Although on the right, they are the distilled image.
Are these supposed to be correspondence because I thought it was kind way with the
Yeah, so basically we randomly select pairs from the original data set. So they are from the original data set. And after the distillation, those are the distilled results. But so we initialize from those data. Yeah. Great. And here we did a few ablation studies. The first one is with and without LoRa on VIT. So we can say that without LoRa, the VIT performance would be pretty bad on Flickr 30K. And with the LoRa matching, it has much better performance. And we also did different vision language experiments on the different vision language encoders. For example, we tried clip text embedding text model, and also for the vision model we use num-free ResNet 50 or RapNet. And later we further explored about the impact of different distillation strategies. So we can compare the text only, image only, and also our co-distillation approach. So our method considers the image text correlation and how they influence each other. So it's worth pointing out that basically it would be impossible if we solely optimize a single modality. So the performance gets a lot worse compared to our co-distilled strategy. So for example, with the same number of 100 training pairs, our method achieves 9.9 for TR, but this is much better than the text only and image only situation. And then last part, we also did some ablation study on the image text pair initialization. So we compared the retrieval performance under different image and text initialization combination. So if we initialize the image from scratch, the performance will be pretty low. And if we, on the contrary, if we just use the noisy text or randomly initialized text embeddings, still with the real image, the performance doesn't drop that much. So the R1 score are 9.0 and IR is the 3.9 here, which are relatively close to our the result we come from the real image plus real text. So this also suggests that the image components plays a pretty important role in this distilled data set. And here's the conclusion part. So by co-distilling both vision and language modalities, we can progressively optimize and distill the most critical information from the original training data set. So our work lays the groundwork for future research that aims at understanding what is the minimum information required for a vision language model to achieve the very comparable performance quickly, and thereby we hope that our work will help build a better understanding for future work on compositionality of compact vision language knowledge. And looking forward, there are certain parts I'm pretty care about for data-centric multimodal machine learning. So the certain parts are optimal data and fundamental scaling and limits, and also scale-driven capabilities. So the key question is, how do we efficiently ensure multimodal data qualities at scale? So the first like optimal data, basically we want to understand what subset of the data are most important for the capabilities of the foundation like multimodal methods, and what kind of synthetic multimodal data we can build. So this is also requires us to better understand how models would leverage the data. And then the second part, fundamental scaling limits. So basically, this is to understand like how much data do we need? Like given a fixed compute budget, is it better to increase the multimodal model size or the multimodal dataset size? And like so. What kind of like information or knowledge is content in the data set we train our model on, and how much of the knowledge is actually needed for our models. And then lastly, about the scale-driven capabilities, so scale-driven capabilities include, for example, like reasoning or in-context learning capabilities. So for this part, we aim to like understand how and why this performance scale with data, compute, and also like model size. So we want to develop a more rigorous understanding of like what increases the scale does to the multimodal training process, and how this desirable emergent capabilities would come up. And that's all of my presentation. All right. Yeah, let me know if you guys have any questions. Oh yeah, so we adopted the course selection methods for basically, let's go back to this slide. All right, so for example, we use the image and text encoders to extract their feature, and then we concat them to find, for example, the dataset center. That's like for the herding part. And for the case center, since we start with like a random sample and find the forest one, we also compute with the concatenated features from image and text features, and find the forest sample.
And how does that compare?
Oh,
I think you this
Oh. Yeah, that's right. So it's definitely like, for example, the herding one would be more like both of them would take less time, but case center is still pretty computational heavy. Yeah, and the performance from what we seen in the experiment section, it performs much worse. Yeah.
Say, for example, you have a trajectory, XP trajectory, you have a different data for the same, but they have different data. How do you like reuse that?
Oh, that's a very good question. So one thing is the expert trajectory does rely on it's like closely associated with like what kind of model we use and what kind of data we use. So I think so the trajectory itself I don't think it will be that useful compared to the data we distilled. So if we can make sure that the data has the cross model or like cross architecture generalization ability, we don't need to reuse the expert trajectory part. Yeah.
I had a question about the results that you showed in the Dora.
Yeah.
I thought from my understanding, that Dora was mainly used to be able to like visually update parameters.
Right.
Why did it give
So basically for the we were looking at the for example, the parameters of the variety base will just be like it will be originally it has like 86 millions. So because one model have this much of parameters, if we want to save a long trajectory, we can imagine that the trajectory will also requires a lot of like we need to save a pretty big parameter in the trajectory. So in this case, we will not be able to have a long like distillation, a large distillation steps, and that affected the performance. Yeah.
So I just make those.
So we can still save the training trajectory, but it will be very hard to like calculate the gradient based on this.
And this concludes the public